Hi, my name is Casey. This is Team EarForce. You'll be hearing from myself, Sofia, Gabby, Maria, and Nick today. So G-induced loss of consciousness poses a significant risk for fighter pilots and has become a big concern for the DoD over the past few years. Specifically, from 1980 to 1999, there were 78 incidences of G-induced loss of consciousness. In the past 10 years, there have been an average of 7 G-induced loss of consciousness incidences, and in the past fiscal year, 12 incidences have occurred, 5 of which occurred in F-16 fighter pilots. Because of these occurrences, the DoD is looking for a device that can monitor pilots in the air. And so as you can see on the screen, this is an example of a fighter pilot actually passing out while turning due to the G-force. And so G-induced loss of consciousness is both dangerous for the safety and well-being of the pilot, but it is also expensive for the military in terms of damaging planes. In order to track these incidences and preemptively avoid them, the Navy and Air Force would like to create headphones that monitor pilots' physiological conditions and their environment. This past year, the DoD posted this idea and this project on their Small Business Innovation Research web panel and mentioned that they are looking for a low-cost way of monitoring warfighter readiness. The DoD already utilizes existing noise-canceling headphones for their pilots, and so they want to take this technology a step forward by monitoring the pilot's physiological status as they fly and measure their readiness. The data that they are looking to collect includes heart rate, body temperature, and pulse oximetry. Ultimately, our end user would be the pilots, and this device would be used both in live flights and in training sessions. So we are looking to integrate sensors into over-ear headphones that are currently being utilized by the DoD. These headphones monitor pilots' data, measure their readiness, and alert them when they are at risk of losing consciousness. We also aim to create this solution at a low cost, specifically under $150, as the DoD was looking for all reusable aspects of the project to be under this price. So now Nick will talk more about our device specifically and how it compares to other products.
Thanks, Casey. Now, when using the device, there are a few straightforward steps to follow to get the measurement data we want. First and most obviously, the pilot puts the headphones on tightly. Meanwhile, ground personnel open the software package and are going to input this pilot data. They'll then be prompted to obviously input the pilot data, and once this is submitted, the people on the ground may simply press the Start Taking Measurements button. The real-time health data will be plotted and continuously updated for constant monitoring. Finally, should pilot health fall out of healthy bounds, both the pilot and ground personnel will be alerted immediately. In terms of competition, EarForce is the clear choice based on the DoD's project requirements. As you can see, the two health and fitness focused devices combine heart rate and temperature sensor data, but neglect blood oxygenation levels, which are crucial in predicting pilot loss of consciousness, another component that these rudimentary devices neglect. Current military headphones do not contain any of the criteria listed in the project description, which is why the DoD commissioned this project to collect all of this data in the first place. For our device specifications, there are a few things to consider to make this device a success. For our device temperature, we require that the cockpit maintain a temperature between -55 degrees Celsius and 150 degrees Celsius, which shouldn't be a problem. Although pilot headphones are typically customized to fit each pilot, it's still imperative to have well-placed sensors so that they work, they don't cause discomfort or injury, and collect correct data. As mentioned, ensuring that correct measurements are collected for the heart rate, pulse oximetry, and temperature sensors is crucial to our device's success. Now, Sofia will talk about the results section.
Great. So moving on to the results of our project, I'll briefly explain our progress throughout the past academic year. So for our proof of concept back in October of 2020, we had successfully integrated all of our sensors onto our first version of our circuit. The images shown are what our circuit looked like at the time, and as you can see, we were still working on a breadboard because we wanted to ensure that the circuitry worked prior to moving to a smaller space. At this checkpoint, we also had the basic setup of our graphic user interface, and while all the large elements were there were definitely large strides that could be made in terms of user experience and aesthetics. For our ugly working prototype in December of 2020, we had switched 2 out of our 3 sensors to different manufacturers and had completed the sensor validation testing for 2 out of our 3 sensors. At this point, we had not yet integrated our circuit with the headset. Lastly, in the spring 2021 semester, we completed all of our sensor validation testing, integrated our circuit with the headset, and miniaturized our device, which mainly meant moving from a breadboard to a protoboard. The images shown below are what our project looks like currently. And additionally, throughout the semester, we took into account some of the feedback that we received from Professor A. Strike, a retired F-16 pilot, and attempted to add a blood pressure sensor to our circuit because we were informed that it can detect deteriorating pilot health with high sensitivity. However, we were unable to integrate a sensor that would work alongside our existing hardware, so we were unable to have that addition. However, this wasn't a huge concern for our team because this wasn't originally stipulated by the DoD's requirements. So now we have a video demonstration of what our product and the graphical user interface look like together. So as you can see, we have our ground personnel putting in the background information of our pilot, Nicholas, who you can now see on the right. He's modeling our amazing headphones. And as you can see, the ground personnel can hit start, and now our device will start to work. That beep that you hear is actually the pilot health being out of bounds. So you can see one sensor was out of range while everything is calibrating. Now, Nicholas will start doing some exercise. So you see his heart rate starts to go up as our project is supposed to show. And now I'll pass it off to Gabby to talk about the validation of our project.
Thank you, Sophia. So this figure shows our heart rate sensor validation. The pale red shading and red line shows the 95% confidence interval and average heart rate using our pulse sensor for 10 trials. The pale blue shading and dark blue line represents the 95% confidence interval and average heart rate of 10 trials conducted using a clinically used heart rate monitor. So because all of our data is within the clinically used confidence interval, the pale blue shaded region, we can affirm that our sensor does give accurate readings. And although it will vary from person to person, the healthy heart rate ranges from a low of 50 when at rest to a high of 180 BPM when performing vigorous exercise. So this figure shows our temperature sensor validation. And after 5 seconds of no contact, the subject's earlobe will interface with the sensor. And the pale blue shading represents the 95% confidence interval, and dark blue line represents the average temperatures for the 10 trials conducted. The internal temperature was measured at 96.5, and the room temperature was at 72 degrees Fahrenheit. So on average, our temperature sensor was 6 degrees less than the measured internal temperature. And because this was consistent across all 10 trials, we can conclude that this sensor does give accurate readings, and we adjusted our healthy bounds for the temperature sensor accordingly. And the healthy temperature ranges from 94.8 to 100.4 degrees Fahrenheit. And lastly, this figure shows our pulse ox sensor validation. So again, 10 trials were conducted and compared against the pulse oximetry readings from a clinically used FL400 pulse oximeter. The 95% confidence interval and average pulse ox readings of our pulse ox sensor is shown by the pale red shaded region and red line. The FL400 gave a consistent reading of 98% for all 10 trials, and because it has a known variability of plus or minus 2%, we can conclude that our sensor gives accurate readings because all of our data was within this variability. And the healthy pulse ox range spans from 93 to 100%. Now I'll pass it off to Maria to discuss our financial strategy and future plans.
Thank you, Gabby. So to start us off, I'll be discussing our financial strategy. So during this process, we quickly discovered that the DoD is spending a large quantity of money in creating customizable headphones for fighter pilots. Therefore, we wanted to create a solution that focused on using low-cost sensors that could be a reasonable and accurate approach to this issue. We matched our goal of staying under $150 mentioned earlier and aim to meet a cost of less than $100 when components are mass-produced and under a government contract. As you can see in the chart, the main components are the headset, the electronics, and the 3D printed material. Now I'll be discussing future goals of the system. In the future, our goal is to integrate our product into existing fighter pilot helmets' inner layers to improve user comfort. We therefore would have to be part of the building helmet process and adjust the sizing of our circuitry if needed, so that they can be integrated into the systems flawlessly. The sensors would be routed through existing pathways of the helmet, and ultimately the sensors would continue to be housed in the earmuffs. The next generation of the system would ensure that future iterations of this product would include sensors that are user tested within the environment that they would be used in, such as flight or training simulations. This would confirm that our device can be used to detect any changes that might lead to a loss of consciousness. Additionally, an updated graphical user face that fits within the current monitoring systems deployed by the DoD would have to be updated. Ultimately, the future generation of these helmets would use machine learning algorithms to predict pilot health based on trends collected by the DoD for each pilot during the training phases of their careers. EarForce team would like to thank Dr. Maltese, Dr. Chow, and Professor A. Strike for their help, as well as the Stevenson Foundation Bioengineering Laboratory. Our team is EarForce, and we would be happy to take any questions at this time.